Okay, so we're going to try a similar kind of problem that has to do with analyzing some data using a story in calculus. This time, we're going to actually not be using a story that is based on an equation, but we're going to look at a story that is actually based on data. So we're going to have some snapshots in time, and we're going to use those in a variety of ways that should kind of lead you down the road that we're probably going to see a Riemann sum and maybe some approximative methods. So let's just kind of see how this thing takes off. So here we go with our image mate. And so here we go. So notice we have this nice little story here, and it's a train that is moving east and west along a railroad track. So it's moving this way right here to the east and the west. According to this, it appears that it has stopped because it had a velocity of 0, and it's moving forward. So to the east at time 2, further to the east at time 5. It's going quite negative here, and so there was probably some value in here, or at least not probably, there should be some value where there would be a 0 in here, and there could be more than that, but that's what we've got. So now here's what we've got is this train runs back and forth east and west, and its velocity, so we're looking at a velocity of the train, not its position, but how fast it's moving. And that it says it's a differentiable function, and that's very, very important because as soon as it says differentiable function, that means that by definition it must also be a continuous function. So what we're going to look at is what is its average acceleration? Well, that goes all the way back to one of the very first things we studied this year. The average acceleration would be the rate of change on average of the velocity function. So we would be talking about the delta v over delta t, or the change in velocity over change in time on this interval 2 to 8, which is simply v of 8 minus v of 2 over 8 minus 2, which we'll go ahead and be grabbing these pieces of data off of here. So v of 8 is negative 120. We're going to do v of 2, which of course is 100, and 8 minus 2 means 6 seconds have elapsed, or 6 minutes have elapsed in this particular story. And so we've got negative 220 meters per minute, which means we've got a negative 110 meters per minute, which we'll usually just write as meters per minute squared. Now, and when we move off of that, it says, do the data in the table, that seems funny to me. It feels like it should say does the data, but I'm certain they've actually vetted this. But it says, do the data in the table support the conclusion that the velocity had to be negative 100 somewhere between 5 and 8? So here's the deal. That's why this word differentiable was added to this story. So does it have to be negative 100 in here somewhere? And I think we should know that the answer is yes, because you can't go from positive 40 in a continuous way down to negative 120 unless you've actually passed through negative 100 on your way. But we have to kind of say that in an intelligent way to show that we understand calculus. So we're going to actually go ahead and say that since v sub a of t is a differentiable function, it is also continuous, and since v sub 8, which is negative 120, is less than negative 100, which in turn is less than 40, which is v sub 5, by the intermediate value theorem, there is some value of t on that interval from 5 to 8, excuse me, that's from 5 to 8, where v sub a of t must be negative 100. Again, since it was a continuous function, it cannot go from one value to the other without passing through that value of negative 100 in its path. Okay, so now all of a sudden we're on to part C, which looks like a pretty lengthy little question here, but we'll see what happens. It says at the time t Ooh, so they give us an initial condition here. They're saying we're starting at 300 meters to the west. So if our station is here, the train is already over here at 300 at time 2. And the train is moving to the east. So it's telling me that it's already at 300 and it's moving to the east. And we're going to go ahead and find out where it is. So they're asking me to find the area under the curve at the value 12. So here's what we've got. We know we already started 300, plus we want to find the area under that curve from 2 to 12 because we're trying to find. And since we already know we're at 2, we're at 300, that's where we're going to start this story, which is kind of how we usually do that. And so this is calculus how we would actually say that, but of course we don't have the actual function that models this data. All we have is, well, numbers. And so it did say that we were going to go ahead and use a trapezoidal rule. So one thing you want to look for is notice that the intervals are not steady. We've got an interval from 2 to 5 that is 3 units wide. We've got an interval from 5 to 8 that is 3 units wide. And then all of a sudden this interval out here is 4 units wide. So what I'm going to do is I'm going to say it's approximately, because this would be the exact value right here, but I cannot tell exactly what this is because I only have these little snapshots. So if I do the average of the two heights, which was 100 for one height, 40 for the other height, here we go, we've got 100 for one, 40 for the other, times how wide that interval was, which is 3, plus the next interval, which was also 3 units wide, and its first base was 40, its next base was negative 120, and our last one, as you recall, had a base that was 4 units wide, and its heights were negative 120, negative 150, and that's going to be an approximation of its position. And again, this is fairly straightforward arithmetic here. And I got negative 150, which because it's negative, that seems to indicate that it would have actually come back and passed the station and been over here a little bit further. So we're going to go ahead and say at t equals 12, the train is 150 meters west of the station. Now notice that I didn't physically show that 100 plus 40 is 140 and then divided by 2 is 70. You could do a lot of that on scratch paper. They don't need to see all of your little pieces of arithmetic. And then the last part, and honestly this is the hardest part of that particular question, is they're talking about the fact that we have train A moving along here, and there's a train B that is traveling north out here. So I'm going to call this X, I'm going to call this Y, and they're going to want to know a little bit about what is happening as the trains recede away from each other, which I guess we could call this thing Z. And since this is east-west and this is north and south, we're going to go ahead and use a little Pythagorean theorem. And so let's see. We know that x squared plus y squared is z squared. And so I'm going to do a little implicit derivative, which is 2x dx dt plus 2y dy dt is 2z dz dt, which of course that's silly. We've got all these 2's in there, so why don't we divide everybody by 2? So remember, dx dt would be the rate at which train A is moving at that moment. Dy dt would be the rate at which train B is moving at that moment. And dz dt would be, again, the distance apart. But we need to know some information there. And one of those pieces of information is we know from above, at time 2, we already knew that it was at 300. So we know that this snapshot in time, this was 300. It tells me right here that this other train was 400. And so they were being very kind to us by giving us X, Y, and Z as 300, 400, and 500, which, by the way, I just noticed that was a 3, 4, 5, so I didn't worry. And so we also know that from the table that dx dt was exactly 100. So we've got that one. So I know x is 300. I know dx dt is 100. I know y is 400. But oh no, what is dy dt? Well, dy dt is actually just the velocity of that particular train. And they actually told me the velocity of the train was right here. So I just need to find v sub b of 2. And if we plug in the number 2, we'd get negative 20 for this portion, 120 for that portion, plus our extra 25 right there. And it looks to me like I've got a total of 125 for that one. Z we knew was 500 from the given information on that 3, 4, 5, and dz dt is the one and only one thing they did not tell me. So if we just do a little mathematics here, we could find out that dz dt is in fact 160 meters per minute. Now, one thing I have not been saying throughout this problem is that this is not a calculator active question. So you'll notice as I went through this problem, and if you want to look back at it, you can, you'll notice that I never actually referred to my calculator, but you'll also notice that as they went through the problem, there's an awful lot of pieces where as you went through that, you actually had fairly easy calculations. Notice 300 times 100, 400 times 125. Of course, I don't think anybody's be shaken too much by dividing by 500. Notice up here, those are not super, super nice numbers, but they're not particularly aggressive, you know, 240 divided by, 140 divided by 2, or negative 80 divided by 2. But that gives us yet another example of how to do that. And so what I'm hoping is that you will actually attempt another one. And your problem that you're going to try is 2016 number 1. And as it turns out, 2016 question number 1, actually, you're going to, sorry, I'm a little out of order here because I had to redo this video, but you're going to do 2015 number 3 next. And when you get on to 2016 number 1, that's actually going to be a calculator. So the one that you're going to have to try to do all the way on your own is going to be a calculator active. So you're probably going to get some slightly different wrinkles, but the concept is pretty much the same. So hopefully you do very, very well. Again, when you do that 2016 number 1, please upload your response as well as the grade that you gave yourself, because I will also post the rubric. It doesn't pay to be dishonest. Just go ahead and tell me how you're doing, because I just want to know how you're doing and if you're actually learning okay. So please let me know if you need help. All right, good luck.